portion of the Hackers project. You saw Kathleen's keynote. You saw something about this. My evenings are free, so this is one of my pet projects. The main point of which is to be able to make this joke slide. But more seriously, so this is a tool that is absolutely inspired by the awesome Quick Check. So let me take you back more than a decade ago to the original paper to tell you about the issue that it addresses. So in the original paper by Hughes and Clausen, they mentioned the experience of one of their early users, Andy Gill, and who said that sometimes the counterexamples are large and it's difficult to understand them. So if I understand correctly, he proposed adding a new method to the type class that's arbitrary that's used by Quick Check. That was originally called smaller, and this is a function from A to a list of A, where by some measure the list of values should be smaller, and these are potentially shrunk values of the counterexample. And so today it's called shrink. Now, taking you to more recently, sometimes this is still a black art, right? How to get good small counterexamples. So this is a post by Eric Koch on Stack Overflow. He was working with the natural language processing algorithm, and even implementing shrink, getting pages and pages and pages of output. And he couldn't figure out. He knew there was a bug, but could not figure out why. So just to kind of give you a preview, I took this is just to give you a sense of where we're headed. So this is from Xmonad, which of course nicely implements Quick Check properties, and this is the core data structure. They use a stack set. So implementing a bug, it's not buggy. I put in a bug. You get something like this, and we can make it smaller by. I don't think that they actually have shrink instances for everything. But doing the same thing, we can get a smaller counterexample. But also, I'll be talking about we don't just give you a single point, a single counterexample, but try to characterize classes of counterexamples. So a number of counterexamples caused by the bug. Okay, so what is SmartCheck? Well, it's really 4 algorithms, and that's what I'll be spending the rest of my time talking to you about. So first, a different approach for doing shrinking of counterexamples, so for reducing them, and then 3 approaches to doing a generalization. What I call universal generalization, existential generalization, and then strengthening preconditions. So let me start. We'll use a running example, and this is actually a terrible example. The reason is because it has nothing. What I'm interested in is very large counterexamples, and these are all quite small, but this is good for pedagogical reasons. So this is going to be a calculator expression language, something very simple. We've got constants, we've got addition, we've got division here. And because I have division, suppose I write an evaluation function where I want to make sure that if I have a division by 0, I'm going to return nothing, otherwise just the value. And so it's reasonable then, I might want to write a property where I say that the evaluator never returns nothing. Of course, I need some sort of precondition, right, to ensure that this doesn't happen. So I might write something like this, where I check that is the denominator in the division, is it a constant, is it 0? And that's false, otherwise it's true, and I recurse through the expression. But of course, because this is about counterexamples, this is not going to hold. And the reason is because I haven't actually reduced this to a normal form, right? I need to run about this. So, clear enough. Okay, so let's look at what shrinking looks like. And we're going to focus, as the example shows, on shrinking algebraic data types. Okay, so this is this expression here is a counterexample to the property I showed you. So it satisfies that precondition, but fails the postcondition. And I'll talk about the size of an expression, and really I'm just counting constructors here. So let me put it in tree form. And the algorithm I'm going to show you, it's actually embarrassingly simple. So it's just breadth first search through the tree, and where we're going to randomly generate strictly smaller values. So let's take a look at this. So I'm going to first, for the first strictly subterm, I'm going to replace it with increasingly larger terms bounded by the size of the term. And so the only thing that's smaller than this are constants. So I'll find actually any constant's going to work here because the problem's in the denominator, right, not the numerator. So let's say I get the constant 1. And so now I've got a new value. So I start the breadth first search over again. And there's nothing smaller than constants. So I move to the next subterm. And we'll do the same thing here. And the only thing smaller again is constants, but because my precondition does preclude having 0 in the denominator, I can't replace it with anything. So I keep going to the next subterm, and I can't replace anything that's smaller, and then the same here. Okay, and that's basically it. So there's a couple of other optimizations in the paper. So what I would love to stand up here and tell you is, I ran the a bunch of benchmarks on the Spec 2000 suite of testing, right? But there is no Spec 2000 suite of testing. I mean, so there's a number of different examples in the paper. This is one from the introduction, and it's somewhat representative. So there's times when this when SmartCheck will generate much smaller values than QuickCheck, also vice versa. So here's one example where SmartCheck's smaller and also generates them quite quickly. So this is the size of the value in the number of constructors and for how graphed against how many runs. One thing I do want to tell you about is if you're using QuickCheck, and definitely consider using the new generics. So it's being QuickCheck's being updated. I think Nick Smallbone is mainly doing the development these days. Correct me if I'm wrong. And he's used GHC generics just like we use, and these for doing shrink instances, and they're quite competitive, probably better than what you'll write by hand. Okay, so a couple of points that I want to talk just before talking about generalization. So really what we've implemented here is in the test community there's a suite of approaches called delta debugging, and this is really just hierarchical delta debugging with randomization. And this isn't really a deep idea, but it's apparently folks have not done this until recently. So the other tool that develops this is actually in the world of finding small C programs that cause bugs in C compilers. So there's a shrinker for C Smith, and they do something similar there as well, specialized for C programs. So you can think of the two approaches as being, as SmartCheck using kind of a top-down random approach versus kind of a bottom-up deterministic approach, because remember, shrink is a function from A to a list of A. And so sometimes shrink, oftentimes the way you implement it, you'll have the same constructors in the shrink instances as in the original counterexample. So you can miss far away minimum examples. However, sometimes in our approach we'll kind of a random approach where we're generating, the only kind of constraint is generating smaller values. We waste time trying to search in kind of a top-down fashion. And moreover, we ignore types at which arbitrary is not defined. So in particular, a lot of times, the kind of values you want to generate are context dependent. So you may not have an arbitrary instance for each type. So this is one of the weaknesses with this approach. Okay. Generalization. So the two of the algorithms are pretty much the same. So they're breadth first search through kind of a greedy heuristic through the counterexample. And the first kind of generalization is it's not sound, but the idea is does every replacement of the subterm cause failure or some proportion? So this is something you can tweak. So let's take a look at this. So if we again look at the first subterm in breadth first search, and let me replace this time with arbitrarily sized terms, and notice that no matter what I replace this with, I'm still going to get a counterexample, right? So I can generalize this, and I say no matter what I replace this with, I get a counterexample. So I move on to the next term, replace it with arbitrarily sized terms. And in this case, I'm not going to be able to do this. I'm not going to be able to always get a counterexample because it has to evaluate to 0. So I keep going in breadth first search, and I can't generalize. So then I get a formula that characterizes the classic counterexamples. And the helpful thing with this is not only the classic counterexamples, but in a large counterexample, I've replaced perhaps a large subterm, which makes it much more readable. Okay. So existential generalization is the idea of can I, for every variant for a sum type, is a counterexample found? So this tells me, is my problem more systemic, or is it rather than just being localized, say, in a particular case branch? So what we're going to do is, again, breadth first search through the counterexample. And actually, one point I want to make is because the universal generalization is stronger than this existential generalization, if I've already generalized a subterm, I'm just going to skip it. So we've already generalized this on the previous slide, so let me skip this subterm. We'll go to the next subterm. And I'm going to replace this with all possible variants from the type. So this is constants, addition, division. And I won't be able to find a counterexample with each variant, right? So namely with constants, it has to be 0, which is precluded by my precondition. But here I can do this. There's a variant there's a possible variant that causes a counterexample in each case. So with constants, addition, division. So they all evaluate here to -5, which causes the property to fail. And similarly, I can do this with this term as well. And so then we can generalize, again, in a different way, the original counterexample by saying that for any of the constructors, there's arguments that cause failure here. Okay. So the final thing is precondition strengthening. And so the idea here is that oftentimes you have a precondition, like I showed you originally, and if this holds, then I want to consider whether the postcondition holds. So let's look at this graphically. So in the case of all possible values, I've got some subset that satisfies the postcondition, something that satisfies the precondition, and what I'm looking for, right, for counterexamples are points in the red circle but not in the blue circle, right? Okay. So I find some counterexamples. And I might be able to characterize them by one of the formulas I was showing you. And what I'd like to do is, in testing, is I'd like to find new counterexamples that aren't necessarily close to the search space of the original ones. I don't want to keep finding ones that have already been characterized over here. Okay. So the way we're going to do this is we're going to implement basically for each of the formula that characterizes a number of counterexamples, a way to say are new counterexamples close to this. So let me just so we'll implement this matches shape function. And so just let me explain this with a couple of examples. So the idea here is that if all the constructors match, and we'll not look at base types like the integers here. If all the constructors match, the two expressions match. However, if I generalize a subterm, then I won't. Then it matches anything. So if it'll take an expression and then a pair where I've got another expression and a list of indexes, say in breadth versus traversal of subterms that I've generalized. And so with E0 and E1, they've got exactly the same constructors. We say they match. E1 and E2, they don't match. But if I've generalized that first subterm, where I add 1 and 2, then it matches anything. And so E1 and E2 match. Okay, so we'll implement this to try to find, just automatically strengthen the precondition. Okay, so suppose I've got a formula characterizing these counterexamples. Then I add this automatically to the precondition and say that I want a new counterexamples that don't satisfy this. And so I might find some more that don't don't satisfy it. I add this to the precondition, and so on and so forth, till I've got a coverage of the state space, or I've exhausted the ability to randomly find new counterexamples. Okay, so the interface then is getting a counterexample. It can come from QuickCheck. It's integrated with QuickCheck to do the counterexample discovery, but you don't necessarily have to use it. We shrink it, generalize it, and then go to 1 to try to find new counterexamples with this strengthened precondition. So does this work? Well, we've done some examples in the paper. I got the code from Eric. with the Stack Overflow question I mentioned originally, and was able to shrink it to something that he was able to find the bug. So it's available on both GitHub as well as Hackage. Okay. So in summary, I just want to make a few points. So first of all, shrinking, I think it's a real problem. So I think it's really well motivated, particularly, for example, with things like giving people bug reports. So like John Rager's work with C. Smith, if they give them a large program to the GCC developers, right, they're just going to ignore it. So you need to have small counterexamples to be able to report these to the developers. And the tool that we have, it complements QuickCheck. It's not a replacement. So these are alternative search strategies, I think ideally you could run them. You could choose the search strategy for trying to find smaller counterexamples. Using SmartCheck should be fairly painless if you use QuickCheck. So we use GHC generic, so you should be able to just derive the instances yourself. And my final point is that shrinking and generalization, it's not enough. So some of the things that I found with looking at very large counterexamples is that a lot of times you get a counterexample where many of the fields are exactly the same, but it makes a very, very large expression. And so, it'd be a great Haskell tool, actually, if I had something where I could give you some sources and it just did common sub-expression elimination for you to make something just simply more readable. So moreover, more tools for taking large algebraic data types and being able to analyze them, pull out subterms, and paste them into your program as you're debugging would be quite helpful. With that, I'm done. Thank you.
Questions?
So that was very cool. How competitive would it be to simply take a quick check like shrinking approach, but just randomly find a bunch of counterexamples? Because as you say, if you find one counterexample and then try to shrink it, you might have gotten yourself stuck on a fairly small hill and thus climbing it won't get you very far. But randomness is a powerful tool.
Yeah, so I don't know definitively, but really it's pseudo-random, right? I could imagine you might get lucky, but this does it a little more systematically.
So what if you had a custom show function for the expression type?
That is bad programming practice. If you want to pretty print something. So if you have a custom, do you mean in what part?
Yeah, so what I mean is that the quick check shrunk counterexample would show it with the custom show function, right? Whereas yours would not, I assume?
Well, so we show data types. We've got a couple of different views. You can show it in tree form or in just string form, but it uses whatever show function is derived or implemented for your data types.
Oh, but when it has the for all.
Yeah. So that's some string hackery. Yeah. Oh. Yeah. So it's terrible. And I haven't tested with perverse strange shows.
So I have a question about the shrinking strategy. So a nice thing when you have the quick checks deterministic shrinking strategy is that you get a counterexample and you know that all the possible shrinkings, which if you wrote the generator, you know what the shrinkings are, none of them provoke the bug. So that tells you something more than just the counterexample. It's the local minimum. Do you have this property as well when you do random? When do you stop?
Oh, right. So okay. So you don't have this property, and when you stop, so you either stop. You set a parameter saying, I only want. So if you have a very deep, in terms of the tree structure, you stop when you get tired, right? You may not want to descend to all the leaves of the tree, or it just stops when it exhaustively analyzes, goes through each subterm of the counterexample. So, but you don't get this property. You're right.
But I guess you could have a hybrid where, at the very end, if SmartCheck gives up, you also try all the normal quick check shrinkings.
That's right. In fact, I mean, it's easier with implementation right now to do it in reverse, where you shrink before you hand it off to SmartCheck. But yeah, absolutely.
But it's a stopping point that's important, right? When it's stopped, you want to know none of the obvious things would still provoke the bug, and that's really useful information to have when you look at the counterexample.
Right. Okay, so it's a good point. Yeah.
I want to make a comment, and I have one question left because Ulf asked the other question. So the comment is, thanks for a very provoking title. You have made a system called SmartCheck. It means that the other system is.
Didn't you see my? Maybe you missed the slide where I said
I had to take a photo. I just the slide where you show the counterexample from QuickCheck and the counterexample from SmallCheck. Is that after shrinking from QuickCheck as well?
I think, if I remember correctly, I don't think that they've implemented shrink for all of the all the types. So absolutely. So I guess two things. So one, I should have use the GHC generic automatic derived shrink instances for that for QuickCheck. That was done before that was implemented. So. Yeah, I mean, do not take that. That was just kind of a motivation.
Oh, okay, that's fine.
There's more proper benchmarks in the paper.
Because what often works with shrinking is you have this sort of the structure way of doing the shrinking that's also implemented in generics now. That gets you a long way. But what really works well in practice in many applications is when you look at a counterexample and say, hey, I wonder if I shrink it in this way, it can be done. You add custom shrink rules.
Right.
And this is what you do in most of these projects. And I guess your randomness gives you a little bit of that, because you, instead of doing the obvious structural thing, you also start doing other things that are actually some smaller inside. So, but I agree. I think what you should do is what Ulf suggested. Just do normal shrinking, and when the shrink list is empty, you also do some random stuff, and then you get best of both worlds.
That's
your
good.
graphs will show strict improvement over the equation. Okay, thanks.
All right. One last question.
So this universal quantification thing, that looks very useful. I wasn't so sure about the stential. I was for some reason hoping that you would, in this counterexample, find out that it was independent of the 5, as long as there's a 5 and a -5, or a 5 in both places. So some kind of correlating sub-expressions.
Yeah, and that is a difficult. I agree that that's a difficult problem, I think, to do in any kind of general setting. Yes, but yeah, it does not try to figure out. But I think that could be related to if you did some common sub-expression elimination first, you might be able to find some sort of relations. But I think that's a hard problem in general.
I guess not that SmartCheck.
Huh?
Not that SmartCheck.
That's right.
I guess the question would be: is it only useful in this particular example where it would be really useful, or is it do you expect it would be generally useful to find these, like say, equal expressions, or is it just this particular example and generally won't be very useful?
Do you mean finding relations between subterms? I don't know.
All right, thank you. And now we have a break again.